All right, so this is page 7, question 7 of the energy workbook. It says if a 1.00 times 10 to the 2 kilowatt elevator motor lifts a 50 kilogram load up by 8 meters, A, determine the gravitational potential energy given to the load. So our power, if we list our givens, is 1.00 times 10 to the 2 kilowatts. And for every kilowatt, there's 1,000 watts. So that means we have 100,000 watts. And then our height is 8 meters. Our mass is 50 kilograms. And another important given is acceleration due to gravity, which is our constant, 9.81 meters per second squared. So part A is asking for the gravitational potential energy of the load. So let's find that using the equation mass times acceleration due to gravity times the height. So our mass is 50 kilograms times 9.81 meters per second squared times height. And that should give us precisely 3,924 joules. So that is the gravitational potential energy of the load. Now, in part B, it says if the elevator motor has an efficiency of 82%, how much energy does it actually use? When it says how much energy does it actually use, it's essentially asking how much energy was actually inputted to the motor. So part B, we need to look at how much energy was actually inputted. And if we have a percent efficiency, then we can correlate that to our percent efficiency equation. So our percent efficiency is 82%. And our percent efficiency equation is equal to the final energy over the initial energy. Oops. And if we have our percent efficiency, however, that means we don't really need to solve for it. And if we have the final energy, because the elevator is moving upwards, that means we're getting our gravitational potential energy. And that means we need the initial energy. So all we need to do is just isolate for E initial, which means moving E initial out of the equation and putting the percent efficiency into the denominator. So E initial is equal to final energy over the percent efficiency. Now, before we put this into the equation, we do have to convert it to a decimal, and that's by dividing it by 100. So that means we're going to take this number up here, gravitational potential energy, 3,924 joules over 0.82. And that number should be approximately 4,785.365 joules. We want to round that off just one more. It could be 4,785 or 80, depending on the rounding. So now we have the actual energy inputted. It'd be useful if we jotted this down. So that's kind of the realistic value we're looking at, because not every system is 100% efficient. There's always some deficiencies. So part C is asking for how long it will take to lift that 50 kilogram object to the height of 8 meters. So when it says how long, it's obviously asking for the time. So we don't know time, but we do know power, which is 100,000 watts. And we do know the energy, which is, as we found out, 4,785.365. We'll use that unrounded value to find the time. Our equation is power equals delta E over delta T. But again, we can rearrange by moving power onto the denominator to isolate for energy. So delta T is now equal to delta E over power. So that means 4,785.365 over joule, 100,000 watts. Calculate it with me. Our number is looking at approximately 0.04785, and we can round that to 3 significant figures, and that will look at 0.048 seconds approximately. And that's pretty much it. That's the entire question. We solved for the gravitational potential energy, and then we looked at the actual energy used when accounting for percent efficiency, and then found the overall time of it.